Hello everyone. In this section, I will talk about handshake interface and synchronous FIFO. These are the context for this section. We'll first talk about handshake interface. I will introduce the protocol of handshake interface. Then we'll talk about synchronous FIFO and how to design a synchronous FIFO and the calculation of FIFO depth. Okay, let's first take a look at handshake interface. As we have said before, for a complex design, we usually divide it into several sub-blocks. Then if the sub-block is still very complex, we will further divide it into small blocks. Then we will design the sub-blocks one by one and finally collect them up. That is instance the sub-modules to make the complex function block, or you can say to make the top block. So this is the method we usually use to deal with complex blocks. So there must be data transfer between each module. Yes, such as you may have data transfer from block A to block B. So how to transfer data? Yeah, you must have the data signal pass from block A to block B. But this is usually not enough because there is invalid data and some cycles. That is, usually we don't transfer data cycle by cycle, and there is some hot cycles. That is, there is low data transfer between block A and block B and some cycles. So how to identify the hot cycles or the NOP, low operation cycles? Then you have to add another signal, maybe labeled as valid. So the waveform will be something like that. If there is data transfer, you assert valid. In this section, all the signals, all the control signals are high active. So you will assert valid high and indicate that this cycle, there is data transfer, and for this cycle and this cycle, there is low data transfer. Yeah. Then you can see, for data transfer from block A to block B, usually you have to use at least two signals, one valid signal along with the data signal. But even with this, sometimes it can't work, because we may occur the situation that block B runs slower than block A. That is, it can't consume data as fast as they produced by block A. For example, block A will produce 90 data every 100 cycles, but block B just can consume 80 data for every 100 cycles. So if you just use valid and D in, there must be data lost at block B. So we need another signal for block B. We use this signal to tell block A that please wait for me for a moment. Please wait for me for some cycles. So you get the handshake interface. So the data source will drive valid and data. Then the data receiver or the data sink will drive acknowledge signal, or you may label it as ready. The ACK signal is used by block B to tell block A that it can receive data at this cycle. So the protocol here is when both valid and ACK is active, a bit of data is transferred between the block A and block B. This is the principle of the protocol for handshake interface. So you can see from the waveform below, the two cycles will transfer data and not for this cycle because the ACK is 0 and the data is transferred at this cycle. So and for this cycle, the valid is inactive, so no data transfer for this cycle. Okay, that's how the handshake interface comes and the principal protocol for handshake interface. And when used in real application, we usually add more restrictions on block A and block B. So these protocols are extra restrictions on block A and block B. Usually we follow these restrictions, but not all the case. So let's check it. First, valid should be honest. That is, when it's assert valid, it must keep valid until a bit of data is transferred. For example, for this cycle, valid is assert high and ACK is low. So this data is, for this cycle, data is not transferred, and valid goes to low in next cycle. So this is not allowed. Usually this is not allowed, or you can say this waveform violate this protocol. Yeah, violate this protocol. The valid signal is not honest. So the right one is you have to keep valid higher, and you can drop it at this point. Then the data will keep the same for this cycle. Okay. So data will be keep the same as data 2. After the data 2 is received or transferred, you can drop valid and change the data to any value. And for ACK, it can be honest a lot. Okay, for the sync, or you can say for the receiver, it's flexible. And when data and producer is valid, it should assert valid. No need to check the status of ACK. For example, at this point, there is the data can be sent by the block A, so it can assert its valid signal. No need to check the status of ACK and this cycle. Yeah, no need to check it. And also for this cycle, there is the data can be sent by block A, or you can say by producer. So it will assert valid and assert the data. No need to check the status of ACK. No matter if ACK is 1 or 0, just assert valid when you want to transfer data. And for consumer, that is block B. When block B can receive data, it will assert ACK. No need to check the status of valid. For example, and these cycles, block B can receive data and this cycle, so it just asserts ACK too high, no need to check this status of valid. For consumer, it's also acceptable for it to assert ACK high when valid is active. That is the waveform here. Consumer can assert ACK high when it has detected that the valid is high. So block B asserts the ACK signal. This is also acceptable, but this may cause one more NLP cycle. For example, this cycle, there is no data transfer for this cycle. Yes. And if block B can assert ACK, just check the status of itself. For example here, when it can receive data, it just assert ACK high. Then there is low wait cycle. When valid is high, the data is transferred. So from the rules, you can see we put more restriction on block A, the producer, but there is nearly no restriction on consumer. And this one is very important. You can imagine this situation. For example, if block A will wait for ACK to 1, then it will assert valid, and block B will wait for the status of valid to 1, then assert its ACK. So if block A and block B will check the status of each other, they may in the deadlock status. That is, when both ACK and valid is low after reset, there will be no data transfer between them. None of them can go high. So they are deadlocked. Okay, that's all for handshake interface. And next, let's look at the synchronous FIFO. FIFO means first in and first out. That is, data that has been first read in will be read out first. So this is the diagram of a FIFO block. Usually it has its I/O signals, clock reset, and this is push. Push is almost the same as write enable, and write data, D in. Then an output signal named full. Full means all the entry of the FIFO has been occupied. For example, if there is 4 entries in this FIFO, and there is already 4 data buffered in this FIFO, then full will be assert. Okay, this is the signal on the write part. For the read part, usually you have the pop signal, pop input. That is the read enable. Then you have the read data output and a flag named empty. Empty means there is no data in the FIFO. Yeah, for example, there is 0 number of data in this FIFO. The empty flag will assert. So you can see the waveform here. For the write part, the waveform is something like that. You can push data every cycle. Push your data. Then when you push data, you have to assert push high. And we assume this is a 4 depth FIFO. So after you have pushed 4 data in the FIFO, the full flag will assert high. And after reset, the empty flag is high. Of course, after reset, there is no data in the FIFO. After one data has been pushed, yeah, then the empty flag will go low, will go to inactive state. And for this cycle, we read the data, we pop the data from the FIFO. So after this cycle, the data number in the FIFO is 3. Yes, in 3. So the full flag will drop. And for this cycle, there is both push and pop. Yeah, this is allowed for FIFO. You can push your data and pop data at the same cycle. So the data number is still 3 after this cycle. Then we push. So the data number will be 4 again. And after that, we pop 4 data out. Then the empty. There will be 0 data after this cycle, and the empty flag assert. So this is a sample waveform for the FIFO. So from the waveform, you can see there is some restrictions for the operation of FIFO. That is, we assume there is a block A, coded A, collected, we'll write to it, and there is a block coded B, we'll read from the FIFO. So there is some restrictions for block A and block B. The restriction is when FIFO is not full, you can assert push high to write your data in the FIFO. But when FIFO is full, for example, when the full flag is asserted, block A can't assert push high. So in these cycles, if we assert push high, you will violate the rule of FIFO. Okay, block A can't assert push high in these cycles, and also for this cycle, you can't assert push high. And for block B, when empty is not assert, you can pop the data from the FIFO. Yeah. And only when empty is not asserted, block B can pop data. So for this cycle, for these cycles and these cycles, block B can't assert pop high. And the data out can validate the same cycle as pop, one cycle later. So both the waveform is acceptable. So when you use the IP block of FIFO, you have to read the data sheet and check what's the waveform for D out, along with pop or one cycle later of pop. This will be easy to understand. When the depth of the FIFO is small, you may use register file. Yes, you may use register file to implement the memory function in the FIFO. So you can have this waveform. Yes, we have talked about register file before. But if the FIFO size is big, you may use SRAM micro. Yes, you may use SRAM micro to implement the memory function inside this FIFO. So for memory micro, the D out must be at least one cycle later after the read operation. So for memory micro, the waveform of D out must be in this format. And please note that FIFO can also have other outputs such as almost full and almost empty. That is, you can set a threshold value for full and empty. For example, for a FIFO of depth 4, you can set the almost threshold value to 2. Then the number of data that has been buffered in the FIFO is greater than or equal to 2. Then the almost full signal will be asserted. And this is also true for almost empty, you can set the threshold value to 1. So the behavior will be when the number of data that has been buffered in the FIFO is less than or equal to 1, almost empty will be asserted. Of course, you can also set the almost empty threshold to 2 or 3. Okay. You can imagine the setting of the threshold value for almost full and almost empty. Maybe use the parameter. Maybe use the parameter syntax in Verilog. Okay, let's think about how to design a synchronous FIFO. For example, if we want to design a synchronous FIFO of 4 depths, how to design it? First, you must have has 2 pointers. Yes, the right pointer and the read pointer. The operation of right pointer is when there is a push, you will increase the pointer by 1. So this will be the address for right operation. And for read pointer, if there is a pop operation, you will increase the pointer by 1. So this will be the read address. So we use 2 pointer to access the memory array. And then how to generate the full and empty signal. Yes, one method is to use an extra counter to count for the valid data number in the FIFO. For example, after reset, the counter is set to 0. Then, when push the data in, it will be increased by 1. If pop data out, it will be decreased by 1. And if both push and pop for the same cycle, it will keep the same. Then you can check the value of the counter. If it equal to 0, you will assert empty. If it equal to the number of 5 depths, you will assert full. This is the logic. And this must be works. But we have to use an extra counter. Is there any way to simple the logic? Okay, sorry. Some number is wrong for the picture, so I have updated the figure below. Okay, let's go on with the generation of full and empty. Some engineers has invented the method of add one extra bit to the pointer. So you can get the full and empty status from the value of the 2 pointers. For example, if we reset, if they both reset to 0, and we push for data in the FIFO, so the right pointer will count from 0 to 3, then go to the value of 4. And in this status, the FIFO is full, so you can say the condition for full is the MSB of read pointer and right pointer is different, and the LSB for the pointer is the same. So in this situation, you will get the full status. So this is the equation. Different at MSB and the same for LSB. And for empty status, if all the bits are equal, you are in the empty status. This is obviously. But if you don't add an extra bit to the counter, you can't get the empty or full status from the value of the pointers. For example, we reset the value to 0 and also write in for data. Then the right pointer will come from 0 to 3, then loop back to 0. You can't tell the full or empty status from the value of pointers. After reset, the counter is the same and they are in empty status, but after we have written in for data, the counter is also the same, but the FIFO is in full status. So add one more bit to right pointer and read pointer will give you ability to generate the full and empty signal. And this method will be simple and use less area than the first method. But if we want to generate the almost full or almost empty flag, then you can figure out how to generate the almost full and almost empty flag. I want to add one more point for synchronous FIFO. From the function of FIFO, you can see the protocol here and the protocol here is something like the handshake interface. Yes. Yes, the push and the full is something like the handshake interface, and the pop and empty is also something like the handshake interface. But the difference is, for FIFO, we put more restriction on block A and block B. Block A can't assert push when full is valid, and block B can't assert pop when empty is valid. So the difference is we just put more restrictions on block B and block A. That is the blocks talk with FIFO. So you can see in this situation, FIFO is a passive block. Okay, let's take a break. In next section, I will show some examples of how to calculate the depth of a FIFO.